Hi everyone, Mr. Hamilton here. This video is about magnetic fields and charged particles. I want to start off with just showing you a short little video segment from St. Mary's University Physics Department where they have the following setup. They have coils of wire on each side here, and then they have this little device in the middle which is going to fire an electron beam straight up. And the question is, what's going to happen to that electron beam as these coils of wire begin to have a current traveling through them? So let's check that out. So what you see is they've put it under ultraviolet light, so you can see the electron beam, and you can see that as they turn the current up in the wires, they're actually able to bend that beam of electrons. Really cool stuff, and actually has some really practical applications for a lot of what we're trying to do in current research. And so this is what we're going to do, and let's actually see the theory behind how that works. A magnetic field will only exert a force on a moving charge. So what we just saw in the video is that we saw electrons that were moving along that beam. The magnitude of the force depends on three things: the velocity of the charged particle, the amount of charge, and the magnetic field intensity. All of this is represented by the equation. The magnetic force is equal to Q, the charge, times the velocity cross the magnetic field. Now that cross, this is called a cross product. Until you've done significant linear algebra and further on in math, you won't understand what that means. For what we're doing in our purposes, is it just basically means that it's going to become a sine. So it's Q, V, B, all the magnitudes of them, sine of the angle between V and B. That's a scalar equation that it converts to, and that's what we're going to use to calculate this. So that scalar equation, if you look at and consider a few things, if Q, V, and B are all 0, then obviously the magnitude of the force in the magnetic field is also going to be 0. Sine theta, if you just consider sine theta for a minute, it's 0. Well, when is sine theta 0? Well, we know from the graph of sine theta that sinus theta is 0 when theta is equal to 0 degrees or 180 degrees. Well, when does that mean about the strongest power of this force? Well, the strongest power of this force is going to occur, strongest force is when the sine of the angle is equal to 1. Well, when does that occur? That occurs when the angle is 90 degrees, 270 degrees, etc. In other words, that the velocity is perpendicular to the magnetic field. That should make sense from the video we saw a minute ago, because we noticed there that the electrons were being fired straight up, so they had a velocity straight up. And then the current that was induced in the coils of wire created a magnetic field that was side to side. And so those two forces were perpendicular to each other. Hence those electrons were so easily able to be bent. Let's just indicate here what each of these are. This was V, this is the charge Q, and this is the magnetic field intensity B. All right, so with those in mind, how do we actually determine what direction this is going to act in? Well, we do that by the right-hand rule. And so here is a picture of the right-hand rule. So you can see here that if your fingers, it's an open hand, and if your fingers point in the direction of the magnetic field, and if your thumb points in the direction of the velocity of the particle, then the force is always in the direction of your palm. Now, obviously this would be opposite if you use your left hand, so it's important you make sure you use your right hand, hence the right-hand rule. Now the point here is that the angle between the speed of the particle and the magnetic field doesn't have to be 90 degrees, but the force will always be perpendicular to both the speed of the particle and the electric field. So keep that in mind. Force always 90 degrees to the other two. So let's write this rule out in words. The right-hand rule for a charge moving perpendicular to a magnetic field has an open hand, and your thumb points in the direction of the particle's velocity. In the direction of the magnetic field lines is what your fingers are going to point into. And your palm faces or points in the direction of the magnetic field. So you should have that written down as your note to indicate that rule. Before we go any further, let's just quickly review magnetic field lines, and then we'll see how this works in a couple of diagrams. You probably remember that magnetic field lines always go north to south outside a magnet. So in this particular case, we have something that looks like this. And so all I'm trying to draw in these first two diagrams here are the magnetic field lines. So there we go. And then here we have from north to south outside this bar magnet. It's going in the direction I'm drawing it in, and then we always put the arrows. These magnetic field lines never cross, and the further you get away from the surface, the more spread out they are. Something like this. And then out here they get more spread out as such, and then here they're getting more spread out as well. And so that's the magnetic field around a bar magnet. Now let's put this in context of the question we're actually dealing with. And so here we have a magnetic field, B for magnetic field, that's going into the page. Remember here that if a magnetic field is going into the page, it's an X. If it's coming out of the page, it's a dot, just like we had for current earlier in grade 11 physics. So going into the page, X, so we have a magnetic field going into the page, and then we have electrons traveling right along the wire. Well, it's important for us to notice there, if you didn't catch it before, let me go up and just point it out again. The thumb points in the direction of the positive particle's velocity. The positive particle's velocity. Don't miss that. If you didn't have that highlighted before, make sure it's highlighted now. The positive particle's velocity. Well, we have an electron moving here. Well, that means the positive particle's velocity is actually in the opposite direction. So we're going to take Q is a negative value, and so in terms of the right-hand rule, we put it in the opposite direction as the electrons are actually moving. And so that means in this case that we put our thumb in the direction to the left of the wire, because it's current carrying wire. We put our fingers pointing straight down into the page, and the force is straight downwards, as we can see there. So it's important that we always put our thumb in the direction of the positive movement of charges, which is always going to be opposite if it's an electron that's traveling. Super important to point that out. So second situation here, we have a magnetic field that's going from the north to south magnets there. And then we have a positive charge that's traveling to the right into this magnetic field. Thumb goes in the direction of that positive moving charges. Fingers go downwards. And so what you should get is you should get your fingers in this direction here. Thumb going, let's try that again. Thumb going this direction. And what you should get, if you're using your right hand, your palm is going straight into the page. And so what that means is the force is into the page. All right, so what does this actually look like in terms of a mathematical calculation? Let's do one example together. This question says an electron traveling at 6 times 10 to the 5 meters per second enters a magnetic field of 0.800 Teslas. If the electron experiences a magnetic force of magnitude 3.84 times 10 to the negative 14 newtons, what was the original direction of the electron's velocity relative to the magnetic field? And you can see if you're using this textbook that I've taken this as number 14 on page 352. Well, let's write down what we're given first. We know it's an electron, so the velocity of the electron, we know only the magnitude of it, is 6.00 times 10 to the 5. We also know that the magnetic field's magnitude is this, and we know that the force is this, the magnitude of the force. What we're after here is the angle between them. And the angle is always in relation to the speed of the particle versus the magnetic field. So let's go ahead and set this up. We know that the force is equal to QVB sine theta. And then really it's just a matter of rearranging this for theta. So FM divided by QVB. And then that's equal to sine theta. And if we take the sine inverse of that, that'll get us what we want. Now it is worth noting here that because it's an electron, if we were given directions, we would have to sub in a negative as the charge, which would change our answer in terms of exactly what side of the angle it's coming from. But because we're just given magnitudes here, we're going to add, whether we put a positive or negative in, we're going to get the same number. One answer is going to be positive, one's going to be negative, but is irrelevant really in this particular question. But before we sub everything in, you'll notice that we are missing one thing, and that is specifically that, the charge on the electron. Charge on an electron is 1.609 times 10 to the negative 19 coulombs, and it's a negative charge. So I'm going to sub those numbers in, and you do the same and see what you get. See if you get the same thing I do. So what you should notice is that when you divide the one very small number by all the numbers that are in the denominator here, this is 10 to the negative 19, that you end up getting a number that's between somewhere close to negative 0.5. And so there you go, you get 0.4972, and so the angle between those is about 29.8 degrees. To 3 sig digs, we get 29.8 degrees. So let's go ahead and summarize that as such. Therefore, the angle between the electron's movement and the magnetic field is 29.8 degrees. Sometimes you'll see this equation represented a little differently, specifically in terms of a current carrying conductor. If we consider, as we did a minute ago, this wire, and we consider electrons or something else traveling along the wire, some charge, let's say that in this case we've got a positive charge moving along that wire, and that positive charge is moving in this direction. Then we have a magnetic field that's acting into the page. Then we can take the length of that wire and do some math around the forces with the length of that wire. And so just using our right-hand rule that we just had, we would say, well, because the charge is moving to the right, positive charge moving to the right, magnetic field's into the page, we would expect our force to be in this direction. And so we can go ahead and take the same equation and just rearrange this given lengths instead of some of these other variables. So let's look at what this looks like. The first thing I want us to note is that current is charge divided by the change in time. This is the charge in coulombs, and this is time in seconds. And we also know that charge is the number of elementary charges times the charge of an elementary charge. And so because of that, we can rewrite current as n times the charge divided by the change in time. Remember from before that we found that the force on one charge is equal to QVB sine theta. But if we have a whole bunch of charges all along this wire, we multiply that by the number of charges that I actually have. So it's n times QVB sine theta. Let's take this one step further. Speed is distance over time, and if you take L as the length of the wire, which a charge is going to travel in a certain amount of time, then you can replace V with L over delta T. And then it's just a matter of rearranging this so we get NQ delta T together. NQ over delta T. Then we have L, B, and sine theta. Taking that one final step, we get I times the length of the wire times the magnetic field times sine of theta. So for a current carrying wire, which is a single wire, this only works for a single wire, what we get is this relationship. And we can calculate things just like we did with the last equation using this one. So super helpful to be able to have this rearranged in this form so we don't have to calculate it over and over and over again for all the charges. We can just consider the length of the wire instead. So I hope that's helpful. If you have questions, as always, reach out and feel free to ask for help.